Welcome to internal energy. So the internal energy, which we symbolize with a capital U, is the total energy of a system. Now, note that we have no way of actually measuring the absolute value of the internal energy. Instead, we can only measure changes in internal energy. So the change in internal energy is delta U is equal to UF minus UI, where UF is the final internal energy and UI is the initial internal energy. So note that throughout thermodynamics, the convention is that a change in a variable is equal to the final state of that variable minus the initial state of that variable. Now, the fact that we can write such a change in internal energy means that internal energy is a state function. It's not a path function. Its value doesn't depend upon the path that we take between 2 points. It only depends upon the initial and the final point. So note that changing any of the state variables like pressure, temperature, volume, number of moles, that will change the internal energy of our system. Now, the molar internal energy, symbolized U sub m, is the internal energy of 1 mole of the substance in the system. So the molar internal energy is equal to the internal energy of the system divided by the number of moles in the system. Now, molecules have a certain number of motional degrees of freedom, such as the ability to translate. This is motion of the center of mass through space. They have the ability to rotate, so motion of the parts of the molecule around the center of mass, and they have the ability to vibrate. So this is variation in the bond lengths and angles of our molecules. So remember from the equipartition theorem of classical mechanics that the average energy of each quadratic contribution to the energy is 1/2 K times T, where K there is the Boltzmann constant and T is the temperature. And this means that the total energy of a monatomic perfect gas, only allowing for translation, because if it's monatomic, then rotation doesn't have any meaning. We're not moving 2 objects around each other. We're just spinning a sphere in place, which really isn't doing anything. We also don't have any vibrations if it's monatomic. There's no variation in bond angles because there are no bonds. So that means that we only have translation. And that means that then if each of our 3 translational degrees of freedom gives us 1/2 kT, that means that the internal energy of the system is equal to 3/2 times N times K times T, where N is the number of molecules that we have. And then we can wrap up N and K to give us N, lowercase n, and R. So now instead of number of molecules, we have number of moles, and R, we have the gas constant instead of the Boltzmann constant. And then if we want to look at the molar internal energy, well then we simply divide U by N, which gives us the molar internal energy is equal to 3/2 RT. Now, that means that the molar internal energy at some temperature T is equal to the molar internal energy at 0. So here, if we don't specify the units on a temperature, it's going to be in kelvins. So the molar internal energy at absolute 0 plus 3/2 times R times T, which means at 25 degrees C for a monatomic perfect gas, 3/2 RT is 3.7 kilojoules per mole. So the translational motion contributes about 4 kilojoules per mole to the molar internal energy of a gaseous sample of atoms or molecules. For a linear molecule, like nitrogen, there are 2 rotational degrees of freedom, 2 axes around which that molecule can rotate. And that means that then the molar internal energy at some temperature T is equal to the molar internal energy at absolute 0 plus 5/2 RT. Now, if we have a nonlinear molecule with 3 rotational degrees of freedom, then the molar internal energy at temperature T is equal to the molar internal energy at absolute 0 plus 3 times R times T. So 6/2 times RT. 3/2 RT are coming from the translational degrees of freedom, and 3 are now coming from our rotational degrees of freedom. Now note here that in comparison with a monatomic perfect gas, a nonlinear molecule then requires twice as much energy to increase the temperature by some amount. And this means that the heat capacity of the nonlinear molecule should be double that of the monatomic gas. Also note that while the vibrational degrees of freedom would increase the heat capacity, the molecules in the gas phase at room temperature do not vibrate significantly, and thus the above can be used as a first approximation. So we can largely ignore the vibrational degrees of freedom when we're looking at heat capacity at room temperature. Further note that the internal energy expressions that we've shown above do not depend upon the volume occupied by that gas. So now let's turn to the first law of thermodynamics. The first law of thermodynamics says the internal energy of an isolated system is constant. So if a system is used to do work on the surroundings and then it's left isolated, then it will never regain that energy to have a restored ability to do work. Once it's expended that energy as work to do some work on the surroundings, that energy is lost to that system forever unless the system regains some energy in some way, either as heat or by the surroundings doing some work on the system again. In other words, there are no perpetual motion machines. Now, the first law of thermodynamics says that the internal energy of an isolated system is constant. Now, if we expand the definition of our system to include everything in the universe, that means that the surroundings are empty. There's nothing in the surroundings. Everything in existence is inside our system. But that means that it's now an isolated system. There's nothing outside of our system, so there's no way for anything from inside the system in the universe to get out of the universe. There's no way for anything outside the universe to get inside the universe, at least as far as we know. And that means that the universe itself is now an isolated system. And that means that the energy inside the universe has to be constant. So if we're moving energy from inside a system, it has to go to our surroundings. It has to go outside the system to the surroundings, but it's not able to leave the universe. So the energy of the universe is constant. Another way of saying this is energy is neither created nor destroyed. We can simply move it from one place to another or one form to another. Now we can also express the first law mathematically as the change in internal energy of our system is equal to Q plus W. Now Q here is defined as the heat absorbed by the system, and W is defined as work done on the system by the surroundings. So, if the system is absorbing energy as heat, then the value of Q is positive. If, on the other hand, the system is releasing energy as heat to the surroundings, then the heat absorbed by the system is a negative value, and that means Q is negative. Now that makes sense because if the system is losing energy as heat, then the internal energy of the system has to be going down. It's losing energy. And that means that Q, the value of Q, has to be negative. Likewise, for W, if the surroundings are doing work on the system, say if the surroundings are compressing an ideal gas into a smaller volume, that means that the energy of the system is going up. Work is being done on the system, so we have a positive value here for W. The internal energy of our system is going up. On the other hand, if the system expands against the surroundings, then the system is doing work on the surroundings, and the value of W here is negative, because work is not being done on the system, work is being done on the surroundings by the system. And this means that the value of W is negative. So when you're looking at heat and work, their values are positive if energy is flowing into the system. Those values are negative if energy is flowing out of the system. Now for an isolated system, the value of Q is 0 because there is no energy being transferred as heat into or out of the system. The system is not absorbing or releasing any heat. The system is also not doing any work, and no work is being done on the system, and that means the value of W is 0. And that means that then the internal energy change is 0. So for an isolated system, the internal energy change has to be 0. Energy of that system is constant. So again, note that Q and W are positive if heat is absorbed by the system or work is done to the system or on the system. Q Q and W are then negative if heat is released by the system or work is done by the system on the surroundings. So Q and W are defined from the system's perspective. They're positive if energy is flowing into the system, and they're negative if energy is flowing out of the system. Now, a system may accept energy in the form of heat or in the form of work, but both will increase the internal energy. That is, the system doesn't distinguish between heat and work. A system doesn't have heat, a system doesn't have work, it has energy. It can transfer that energy to the surroundings either as heat or as work, but that transfer is just going to affect the balance of energy remaining in the system. So that was internal energy.